So we need to talk today to finish up this chapter. This is 4.4. We're going to do derivatives of logarithms, exponentials, and super exponentials. You know how we have superfoil? We have super exponentials too. So we're going to review how to take those derivatives. Trung, if you're watching this video, we miss you. We hope you are having a good time out of Joshua Tree. Okay, let's start with logarithms. If y equals the natural log of a, then how do we take its derivative? So then the rule is that dy dx is, all right, do you remember from last year? This was a fraction one. 1 over a times dA dx. Okay, that's for a natural log. Now what if it's not a natural log? So if y equals log base b of a, then the derivative on that is still 1 over a dA dx, but additionally 1 over the natural log of b. So that will work on the natural logs as well. You just have 1 over natural log e, which is 1, so it doesn't change anything. So that is the rule. So if I were going to say just memorize one of them, memorize the bottom one because it works for both. The top one only works on natural logs, the bottom one works on both. So that's how to do logs. Okay, then if we have exponentials, if y equals an a to a power p, then dy dx equals, all right, so the rule is you start with a to the p itself. Then what comes next? The natural log of whatever the power is. No, not of the power. Natural log of a, whatever a is. And then dp dx, the derivative of the power. So the a to the power itself, then the natural log of a, which is the base, and then dp dx. So that's the rule for exponentials. And then the last one is the rule for super exponentials. Okay, if y equals q to the p, and q is not constant. So this is a little different. In the question above, maybe we put a is constant. And so if a is constant, then you can apply that rule. But what if the bottom is not constant either? Okay, no. So if you've got, then that's what we call a super exponential, where the bottom has a variable and the exponent has a variable. So that's a super exponential. So then we use what we called last year logarithmic differentiation. So last year we did all of these on separate days. We did exponentials one day. We did logs one day. And then we did logarithmic differentiation another day. Today we're doing it all together. Logarithmic differentiation says take the natural log on both sides first. And you just do the order, logarithmic differentiation. So take the natural log on both sides first, and then take the derivative on both sides. And once you've done that, you can solve for dy dx. So that is called how you treat a super exponential with the process of logarithmic differentiation. So we're just going to do sample problems. I have several. I've got 1, 2, 3, 4, 5, 6, 7. We don't maybe not need all 7, but some of them were easy and some of them were hard. So let's start with an easy one just to get our brains warmed up. So y equals 3 to the x squared. Okay, that's an easy one. That is just an exponential because the bottom is constant. So dy dx equals 3 to the x squared. So you just copy it. And then times the natural log of what number? 3. And then times the chain rule. So I'm going to add on to the end 2x. So that's the easy one. All right, Tom, you feel like you're warmed up? Eating? How about you? Not yet. All right. Am I going too fast? A little bit too fast? A little bit. Okay, let's try another one. Y equals e to the sine of the square root of x. Eating, do you want to try it, or do you want to have somebody else try it? You'll try it? All right, good girl. Okay, e to the, great, times the natural log of e, which is going to be 1. Yeah, the natural log of e. Okay, times very good, cosine square root x times awesome, awesome, 1 over 2 square root x, so the derivative of the square root of x. So beautiful. And so the only thing we would do is clean up that the natural log of e is 1, and then you have it. There's nothing else we can do to simplify that. Okay, awesome. Any questions on plain old exponentials? So let's try some logs, and then we'll get into the super exponentials, so where we need logarithmic differentiation. So let's try y equals the log base of 4 times the quantity 2x minus 1. So I'd put this into the category of pretty easy. So the derivative of dy dx is going to be 1 over. We start with the expression 2x minus 1. Then we multiply by 1 over what natural log? We have, boy, natural log of what? Okay, Tom, do you know? What natural log? Okay.
Should be 4.
Natural log of 4, because that's the base. And then we finish with the derivative of the inside, which is just the number 2. Now, how can we simplify that? All right, well, the natural log of 4 is 2 ln 2. That's what 4 is, because 4 is 2 squared, and you pull the power to the front, and then times 2, so that allows you to reduce the 2's. And so we're left with 1 over the quantity 2x minus 1 and the natural log of 2. Okay, one more practice with logarithms. Okay, boy, I'm going to have you practice this one, okay? The natural log of 1 over x. Give you a minute to copy that. Okay, for logarithms, we start with 1 over. So what will we have? 1 over.
1 over x.
Yeah, 1 over x. All right, very good. 1 over x times
dx. 1 over 2 square root of x.
say that again. Negative negative x to the negative 2. Okay. All right, so let's clean this up. Negative x to the negative 2. Well, what's 1 over x? Look, how can we write that? That's just x. And then what is negative x to the negative 2? Negative 1 over x squared, right? And so what will that simplify to be?
Negative 1 over x.
Very good. Okay. Okay, any questions so far before we start doing some super exponentials? Okay. All right, let's try some super exponentials then. Okay, Aubrey, I'm going to have you do this one. All right, y equals x rad x, x to the rad x. We call this a super exponential because the bottom is a variable, the base is a variable, and the exponent is a variable. So we're going to use what's called logarithmic differentiation. So the first step is to apply the log.
So the natural log of y equals the natural log of q to the p.
Okay, so the natural log of y equals,
The natural log of q.
which would be the natural log of what to the what?
It would be natural log of, oh, it'd be p natural log of q.
Right, but for this problem.
Oh, I'm sorry.
So the natural log of x to the rad x, okay? So what do we do after we've done that? How can we clean that up? Not yet. There's one thing you got to do before you jump. Okay, I want to bring the rad x to the front. So I'm going to have rad x in front of the natural log of x. So that's what you want after you apply your log. And I shouldn't really write log. I should write apply ln. Okay, that's what we want. We want to apply the natural log. Okay, which we did. All right, now we are going to apply the derivative. All right, so take it from there. What is the derivative of the natural log of y?
1 over y dy dx.
1 over y dy dx. Okay, and then what? Not chain rule. That's multiplication. So what rule is that?
But that's the product.
The product rule. Okay, we want product rule. Okay, so go with it. Go for it with the product rule.
Over 2 rad x.
Okay, so 1 over 2 rad x, natural log of x, plus
Rad x.
rad x.
Times 1 over x.
Very good. So let's see. We've got 1 over y dy dx equals the natural log of x over 2 rad x plus rad x over regular x, which can be simplified. I think I'd rather write that as 1 over rad x. How do I add those two quantities together? I need a common denominator, so I'm going to need 2. So I'll have 1 over y dy dx. Now with the common denominator, I can write 2 plus the natural log of x over the common denominator, 2 rad x. right, our last step is to solve for dy dx, or get dy dx alone. Okay, so we're going to multiply by y, so dy dx would be y times the quantity 2 plus the natural log of x over 2 rad x. And what was y to begin with? X to the rad x. So we finish this by saying x to the rad x times the quantity 2 plus the natural log of x of 2 rad x. So it's not this majorly complicated thing. You just have to be careful each step that you're going, that you're following the procedure. I want to do another one of these super exponentials with you. Tom, how about you take the lead on this one, okay? All right, he's ready. All right, so let's do y equals secant x to the tangent x. Okay, all right, so this is a super exponential, so we're going to apply the natural log. All right, go for that.
So natural log y equals to natural log secant x to the
Are you okay if instead of writing that, if I just go ahead and move the tangent x to the front and then have the natural log of secant x to save me a step?
Yeah.
Okay. All right, so we have taken the natural log, which allows us to pull that power down to the front. Okay, now we're going to apply the rules for derivatives.
So on the left side, that should be 1 over I times dy dx.
Okay?
On the other side, so it should be tangent x times one over secant x times secant x tangent x plus secant square x times natural log secant x.
Phew. Nicely done.
And then dy over dx is,
Well, can we simplify anything in there?
yeah,
What can we simplify?
so those are secant x and reduce.
All right, the secant x can reduce. All right, so he's ready to go to dy dx now. Okay, dy dx equals
Tangent square x plus secant square x times natural log secant x.
tangent squared x plus secant squared x times the natural log of secant x.
And the entire thing times secant x to the tangent x, which is y.
All right, and the entire thing multiplied by y. So then we finally end up with secant x to the tangent x times the whole quantity of tangent squared plus secant squared, the natural log of secant x. Whew! Nice job.
This is a long.
Okay, last one. I want to show you sometimes logarithmic differentiation so sometimes that process that we were just doing, it can help us avoid the quotient rule. The quotient rule is not my favorite because you've got b times a prime minus a times b prime all over b squared, and it's not necessarily my favorite. So sometimes if you're looking at the quotient rule, and here's a question. How'd you like to find the derivative of that? Not only are you going to need the quotient rule, but what else would you need within the quotient rule? You're going to need the product rule because x cos x is a product. So you're going to need the quotient rule and the product rule. So sometimes you're like, ooh, try logarithmic differentiation instead. So apply ln. So that gives you ln y, and it gives you ln of x plus 5 over x cos x. And there's a rule for the logarithm of things that are divided. So this could be the logarithm of x plus 5 minus the logarithm of x and minus the logarithm of cos x. You can separate the quotient and the product. Right? You can separate all of them, the quotient and the product, and it's a lot easier to take all those derivatives than to do the quotient rule. So once you have that, now you can apply the derivative. And so the derivative is going to be 1 over y dy dx, and then each 1 over x plus 5, and 1 over x, and 1 over cos x times negative sign as your chain rule. You don't have to, it doesn't take as much brain power by avoiding the quotient rule. So we have dy dx equals y times the quantity 1 over x plus 5 minus 1 over x plus tan x, because sine over cosine is tan x. And then you can change y. And you can replace y with the original expression. So x plus 5 over x cos x. And then 1 over x plus 5 minus 1 over x plus tan x. That's just a lot cleaner of an answer than the quotient rule.